For Chapter 17.2 Reassessment, I use examples from the book. For this first problem, I have a thin spherical shell made of plastic, which carries a uniformly distributed negative charge, Q1. There is also a thin circular disc made of glass, which carries a uniformly positive charge, Q2. The radius of the plastic shell is very small compared to the radius of the glass disc. The radius of the glass disc is also much bigger than the distance from the surface of the shell to the surface of the disc. For this problem, I need to find the potential difference from the center of the shell to the surface of the disc. Because there is very little matter in both the shell and the disc, I will ignore the polarization of the plastic and glass. By using the superposition principle, I know that the net electric field equals the electric field of the shell plus the electric field of the disc. And by using the delta V equation, I am able to set up an equation for the total change in potential by adding the contributions of the shell and the contributions of the disc. I first started with the shell. I broke this part of the equation up into two components, the part inside the shell and the part due to the surface. The first is the electric field inside the shell, which from previous chapters I know that the electric field inside the shell equals 0, which leaves me with the second component of the shell, which is from the surface to location 2. The electric field due to the surface of the shell equals 1 over 4 pi epsilon naught times the charge, negative Q1, divided by x squared. And because it is a straight line from 1 to 2, I know only one variable of the delta L vector is changing. And also because in this problem I chose to align my x-axis through these two locations, I know that delta L equals a vector with only delta x changing. Now I am able to set up and solve the interval from the surface of the shell to location 2, only due to the shell. This interval equals the electric field due to the surface, where x starts at R1 and goes to R1 plus d. Next, I can find the contribution made by the disc. Because the radius of the disc is so much larger compared to the distance between the two locations, the electric field due to the disc is approximately the charge Q2 divided by the area divided by 2 epsilon naught, which means that V2 minus V1 of the disc would simply equal the electric field of the disc times R1 plus D. Now I can use these two contributions in my first equation to find that the potential difference from location 1 to location 2 due to both the negatively charged shell and the positively charged disc. If I had a metal sphere of radius 3 millimeters and charge negative 2 nanocoulombs, I could find the potential at a location C, which is 5 millimeters from the center. Since potential has a value at every location in space, potential forms a scalar field. The potential relative to infinity is illustrated by Vc equals Vc minus V infinity, which also equals the negative interval from infinity to C of the electric field due to a point of charge where x is changing. By solving and plugging in the values of this situation, I was able to find the potential of a metal sphere of radius 3 millimeters and charge negative 2 nanocoulombs at a location 5 millimeters from the center of the sphere to equal negative 3600 volts.